And here we go. Questions about the class? You guys saw the next homework 3 is posted. Generally, I try to make the homeworks cover material that we cover by Friday of the previous week. Hopefully you guys have noticed that at this point. So just a quick review then over what we've been doing over the past few days. We talked a lot about conservation laws and you know, constitutive equations and stuff like that. And we end up deriving this set of equations. They're called the Navier-Stokes equations. They're quite complicated, but what we had was a general recipe for solving them. And this is a recipe that we started off on Friday in solving sort of our first flow problem. Write down equations, boundary conditions, simplify the problem by thinking about it a little bit. And then what we're going to do today is steps 4, 5, and 6, basically solving the differential equations and then evaluating the solution. And so here's where we were on Friday. We were talking about basically a sheet of fluid that is up against a wall like this, or up against some sort of hard surface, and it's flowing down through the assistance of some sort of gravitational field. The equations we already wrote down in the previous section. And so then we were playing with the boundary conditions a little bit. We talked about the no-slip boundary condition, basically just along a solid surface, the velocity is equal to 0. And then at y equals 0, at this air-fluid interface, just through arguments of stresses and stuff like that, we found that the derivative of like that these stresses are equal to 0. You can call this the no-stress boundary condition, if you will. Okay. Then we were able to just use a few relatively simple assumptions. For instance, that there's no velocity in the z direction and all derivatives in the z direction are 0, it's steady, et cetera, to basically simplify the Navier-Stokes and continuity equations down to this. And then we were able to simplify that even further by looking at pressure arguments and stuff, and about how pressure is constant everywhere and stuff like that, to get to this very simple equation, and then these two boundary conditions. Okay. And so then the game today is basically just to solve this differential equation, and that's step 4, right? So step 4 is solve. And then we're just going to play with this solution a little bit more and just think about what the different implications are. Okay, any questions at all about how we got to this point? As I mentioned a little bit on Friday, this is maybe a little bit more rigorous, and I'm not going to ask you to go through this level of detail through everything, as long as you can mostly justify how you got to things and stuff. For instance, it'd be helpful if you can write down these different assumptions that you're using, of course. Then it makes sense how you are able to go from the complicated Navier-Stokes equations down to something that's relatively simple here. Okay, and now it's just a matter of solving this differential equation. Step 5, if you recall, was that if you can't solve the differential equation, then you need to approximate. We're likely not going to have to do that here, right? This is a fairly simple differential equation. One thing I should mention when you that you should check is that your boundary conditions and the equations actually match up. Here's what I mean. For every derivative in your original differential equation, you need to have one boundary condition. And so in this particular equation, you have 2 derivatives in y, and so you need 2 boundary conditions in y, and that's why we have 2 boundary conditions in y. One that's evaluated y equals 0, one that's evaluated y equals h. And now it's just a matter of solving this differential equation. Okay? And most of you guys already know how to do this. If you don't, you just integrate this equation twice. So dvx dy is equal to minus rho g over mu times y plus some integration constant. Once we integrate this once, actually, we can already apply the second boundary condition. The second boundary condition, which says that this derivative is equal to 0 when y equals 0, and so therefore c1 is equal to 0. And then we integrate one more time to get vx is equal to this. Okay, and then you apply boundary condition 1, plug in a y equals h here, and then plug in a 0 over here to find what c2 is. You'll find that c2 just looks like this. Okay. And so that means that the overall solution looks like this. It's just Vy is a function of, Vx is a function of y, it's just equal to this. And I like writing it like this. Hopefully this, this way of writing it lets you see that this is just going to look something, this velocity profile is going to look something parabolic if you had to plot it, or at least draw it in the geometry that we're dealing with here. We're talking about something that looks like this, right? Where y starts at 0 here and increases in that direction. Okay. No step 5 again, because we're able to completely solve this equation. But step 6 is basically just to play with the solution afterwards. So analyze the solution. Okay. Things that, so basically just very quick sanity checks, for instance. Does this satisfy the boundary conditions? Right? Just to remind you, the boundary conditions are that Vx is equal to 0 at y equals h. That's what we see here. It seems to satisfy that, right? When y equals h here, you plug in a y equals h, and you get 1 minus 1, so it's equal to 0, right? And then at y equals 0, you have that it's flat like this. And here you'd have to actually take the derivative and stuff and verify it, but trust me, it actually does work out. You should get in good practice of actually plotting your solutions and just making sure that they actually make sense, right? We can also go further, for instance. We can calculate the volumetric flow rate. Okay. In a lot of fluids problems, the textbook will ask you to do this. One of the reasons that you do this is because that's sort of what's measurable, right? You know, it's difficult to actually, well, it's not difficult. You guys saw the video online on flow visualization to visualize what the flow would look like. But to actually, like, the experiment that you can do to test what we calculate here is to basically just take a cup under the wall and actually start collecting it, right? And so that's why a lot of times fluids problems ask you to do this. The volumetric flow rate is just the surface integral. Sorry, that's supposed to be 0. The surface integral of the velocity in whichever direction it happens to be going, right? And so remember, x is going in that direction, and z is going in and out of the screen. And so I was assuming that there's some sort of width of this wall that shouldn't really matter because everything's invariant in z anyway. And so it's just a matter of taking this integral. That integral is fairly easy to calculate. I'll just do that in one step right here. You can multiply this out and then take an integral. You get something like this. Sorry, that's supposed to be a 2. Integrated or evaluated from 0 to h. Okay. And then you get something like this. And again, this is a testable experiment, right? You know, you could potentially somehow control the thickness of that film of the h, and then you know, calculate what the flow rate would be, and then, you know, plot it and make sure that it actually does follow a 1/3 dependence or something like that. Or you can change the viscosity, the density, et cetera, right? Something that's perhaps more interesting is looking at the shear stress distribution. It's interesting because this shear stress idea is something that we just introduced not too long ago. And perhaps it's something that's still a little bit new to some of you. Let me go ahead and write out what the shear stress that I care about right here is. Think about this term, delta or sigma yx. And we're talking about shear stress, so we don't need to worry about pressure. And so you can look at the shear stress tensor. Those two should be the same thing, right? Sigma yx and tau yx should be the same. And according to Newton's law of viscosity, well, this is just mu times dvx dy plus dvy dx. Okay. And so in this particular problem, we don't have a vy, so we don't need to worry about the second term. This vx right here, we can calculate from this. Okay, so it's just taking a derivative of this with respect to y. If you do that, what you will find is that the shear stress distribution looks like rho gy. Okay? I don't know if that's meaningful physically to any of you guys, but let me just try and explain what this actually means, right? If you recall from your notes a long time ago, it's going to take me a second to page through, and so I'm not going to do that. But the interpretation of this shear stress component means, let me write it out in a sentence, sigma yx is, if I can write is, the x component of the force on a plane normal to EY, right? And that's exerted by the fluid at greater y acting on the fluid at lower y or lesser y. Okay. It's kind of a, let me now actually do some drawings and stuff and try and explain to you what this actually means. Okay. Here's my wall. Okay. Remember our axes here, this was y and this way was x, right? And so what this means is if I have, let's just say, a surface somewhere here, like that, somewhere in the middle, it's supposed to be in y. It's supposed to be, perpendicular to y, right? It has a normal vector EY like that. Okay. This is the x component of the force on a plane normal to EY. So here's my plane normal to EY, exerted by this fluid over here at greater y on the fluid at lesser y here. So it's basically, if I draw a plane right here at, let's say, any particular position, this is a field, right? And so it varies with respect to position, right? If I draw a plane right here, how much force is this fluid over here exerting on this fluid? And the answer in this case is rho gy, y being however far I am over here, times rho g, and negative. So negative means it's going in the negative x direction. So this particular force might look something like this, right? The stress vector here might look something like this, right? Does that kind of make sense physically? Can anyone sort of either Zoom or in the room kind of intuit why it would look like that? Why, for instance, the S would be pointing in the upwards direction here?
The way that I thought about it was like because of Newton's third law, right? Like each fluid element layer, I guess, is like pushing on every adjacent layer to the right, right? Which
Can you
means
guys in the room hear him when he's saying that, even in the back? Or do I need to repeat? You can hear? Okay, cool. There's quiet enough in the room. That's sweet. Yeah, so Nikhil said something about Newton's third law. AJ, go ahead. When you say this side or this side, you're talking about the fluid's moving faster on this side.
On the side to the right of the plane and on the side to the left of the plane.
Uh-huh.
So because there's like because there's some friction or there's some like force on that plane from the fluid moving and it's moving faster on this side than on this side. There's a net force.
Yeah, so AJ is saying basically, I'm trying to repeat and paraphrase what he's saying. There's the fluid over here on the right side. You guys see my mouse over zoom, right? On the right side of this plane is moving faster than the fluid moving on this side, on the left side of the plane. And so you can imagine there's some sort of shear force that counteracts that, and that's what this is. That's what this S is, right? Yeah, that all kind of makes sense. Let's think about this. Let's think about this even in a more sophisticated way. What if I decided to draw my plane over here? Would you guys envision that this S vector, this force, would be, well, it should still be going in the same direction, right? It should be negative. Should it be smaller or larger in magnitude? Smaller. Someone in the room said smaller. How did you know that? Yeah, because you're cheating, because this is because it's the sigma yx is equal to negative rho gy, and so here y is smaller, and so therefore my s is going to be smaller if I can draw a smaller s without messing up somehow. Here, I'll just draw a smaller s like that. Okay, and then of course, by analogy, over here, we should have a really, really large s, right? Okay, that all kind of makes sense. But it turns out that we can go even farther than this, okay? When I draw a surface right here, let's say at a position y, right? X and z don't matter, right? Everything is just invariant in those coordinates. How much does the fluid to the right of this, how much does the fluid to the right of this surface actually weigh? What's the weight of that fluid? Any ideas? It would just be the mass of the fluid to the right of this times g, right? F equals mg, okay? So the weight of the fluid to the right of, I'll say, a plane at position y. That's equal to, again, m times g, right? M here is going to be the density of the fluid times the volume, right? So the volume of the fluid to the right here would be some sort of area of this surface, let's say, of whatever plane I drew. So times A times Y, because that's how much fluid is to the right, right? So that's the mass times G. Okay? Do you guys kind of see what's going on here? This is negative rho gy. This is, I guess I could rewrite this as rho gy a, right? And so the size of these forces over here, this is a force per unit area, right? And so here's the area right here, right? And so what this means is that the shear stress exactly counterbalances the weight of the fluid closer to the air, right? Isn't that kind of cool how that exactly works itself out? It makes a lot of sense because everything is steady, and so there can be no acceleration, right? And so all the force that's exerted at any given point has to be exactly balanced by the force on the other side, kind of like what Nikhil was saying over Zoom, Newton's third law. But we can actually calculate exactly how much force this side of the fluid or this side of this plane exerts on this side of the plane. It's just the weight of the fluid. And so therefore it has to exactly counterbalance itself out, right? So this is the sort of analysis that you could imagine that like this could be a part C in a problem or something like that, right? In a homework problem. You could totally see me having fun and writing a homework problem looking kind of like this, right? Cool. That's as far as I'm going to go in analyzing this. The one thing that I'll mention sort of independent of this problem is uniqueness. Okay. I'll just say the only thing I'll say in here is that this solution is not necessarily unique. Okay. Particularly as V gets large. Okay. Once that starts to happen, you could imagine that several of these assumptions that we made up here, all these assumptions over here could start to break down, right? It could potentially not be steady. You know, you could have like little eddies going on in there. You could have things actually changing in the Z direction, or even in the X direction or anything like that, right? You could imagine even that in this sort of falling film example, you could have surface effects or something if the surface is no longer flat. And perhaps some of you guys had a chance to, I don't know if anyone has had a chance to watch the videos that I sent out that talks a lot about surface tension and stuff like that. And you could imagine that's starting to play a role at in some length scales and some regimes as well. Okay. Questions on this? Our first fluids problem that we've solved, and actually made sense and tied up all the loose ends in and stuff like that as well. Right?
Hi, Mitchell.
Yeah.
What do you mean by the solution is not necessarily unique? Do you mean there are multiple solutions that can describe the this problem, or?
Yeah. Everyone in the classroom heard that, right? All I mean is just that this particular solution happens to work in this particular regime where we were able to apply these assumptions. If some of these assumptions just like had broken down, right? So if all we started with in this particular solution is just the Navier-Stokes equations and the boundary conditions, then there could be many other solutions that could potentially happen here. The only reason why we're able to get down to this one unique solution is because of all these assumptions that we imposed, right? That's all I mean when I say that. And so all I'm saying is, you know, for most of this class, we will get you to a unique solution that you can write down, hopefully, and analyze and stuff in the same way that that we've been doing here. But there's no guarantee in the real world that that's what could potentially happen. Okay.
Thank you.
Let me introduce the next concept then. To get us to solve even more complicated things, we're going to talk a little bit about curvilinear coordinates. You guys have almost certainly seen this before, things like cylindrical and spherical coordinates, right? I'm not going to devote an entire lecture about this, but I do know that we've talked a lot about different vector calculus concepts and stuff, and so I just need to close the loop on some of those when we're dealing with things that are not Cartesian. So let's say we're talking about cylindrical coordinates starting off. Okay, so you guys have almost all seen cylindrical coordinates. When I draw a diagram like this, hopefully you will have seen it. So again, here's my 1, 2, and 3. But here we're not going to call our 1, 2, and 3 in that direction anymore, so I'll just leave those blank for a second. But you know that any given point, for instance, let's say a point right here, the way that you define this particular point is you have an x position, or sorry, you have a z component to this point, a z position that defines this point. That's given by that z right there. And then, of course, you have a radius, and then you have an angle theta with respect to the x-axis, and that's what defines that one point, right? So basically, a point at x, y, and z can also be defined as r, theta, and z. Okay? And the way to convert that, you guys have probably seen this before too, is that x is defined as r cosine theta, y is defined as r sine theta, and z is just the same thing, it's just z. Okay, and if you haven't seen this before, hopefully you can just intuit out how this actually works, right? R times cosine theta is just the x component over here, and r times sine theta is the z component, is the y component over here. Okay. Perhaps something that you guys have not seen so far with cylindrical and spherical coordinates is the unit vectors, right? We've been talking a lot about unit vectors. They're sort of the basis of index notation and everything we've been talking about with gradients and curls and divergences and stuff like that. And so those become really important in cylindrical coordinates as well, and all sorts of different coordinate systems. In normal Cartesian coordinates, we think about the unit vectors as pointing in the x, y, and z direction, right? That's exactly how unit vectors are defined here as well. In the r, theta, and z direction, except there's no r, theta, and z direction. Those are just coordinates, right? And so by convention, basically, unit vectors always point towards an increasing coordinate. Okay, that's what it meant to say EX and EY and EZ are in the X, Y, and Z direction. Though they're pointing in the direction where X is increasing or Y is increasing or Z is increasing or anything like that, right? That's basically what we're saying here as well. Okay, the difference is that there's no universally defined R direction or universally defined theta direction. These unit vectors actually depend on where you happen to be. The unit vectors are not constant anymore, okay? So they're no longer constant. And depending on where you are in space, you can write down what those unit vectors actually are, okay? For example, ER can be defined as cosine theta EX plus sine theta EY. Okay. And you can, here I'll write down the other ones. E theta is equal to minus sine of theta EX plus cosine theta EY. And of course, EZ is just equal to EZ. That does not change. Okay. Now, these are a little bit more tricky to derive than these sorts of things, like what I'm showing up here, like the changing coordinate systems from different points and stuff. Those you could probably just intuit if you remember a little bit of trigonometry, like how the x component here is just r cosine theta, et cetera, et cetera. This actually works out too if you think about it geometrically, but it's easy to forget. Like for instance, it's very easy to forget this minus sign right here. Let me make sure that minus sign is more clear and you guys don't think that that's just some sort of slip of the pen. Okay. But perhaps you can convince yourself that these unit vectors actually do work. If they don't, just look them up. All right, that's just the easiest way to think about it. Okay. But just at any given point, this ER always points in the direction of increasing R, and this always points in the direction of increasing theta. Okay. And of course, these are unit vectors too, right? You can imagine, you can see that the magnitude of this vector is cosine squared theta plus sine squared theta, which is equal to 1. Right? All kind of makes sense? Okay, the reason why we use these unit vectors is because, well, they provide a whole other different coordinate system that we can use to define every vector. Remember, every vector can be expressed in terms of the sum of unit vectors, okay? It's just in this case, those unit vectors actually depend on where we are with respect to position, right? In order to define any sort of vector as a sum of components of unit vectors, you have to realize that unit vectors are always orthogonal, and that's still true here. Okay, in other words, EI dot EJ is just equal to delta IJ, right? And hopefully from here you can kind of see that that's going to be true. And if you don't believe me, then you can dot ER and E theta here, and you will see that that's actually true, right? If we were to dot those very quickly, you would see you'd have cosine times negative sine plus sine times negative plus sine times cosine, so that's equal to 0. If I were to dot ER and E theta. Okay. You can also do a cross product. I'll just say cross product works too. But the order of unit vectors follows, man, I can't write today, follows the right-hand rule. Okay, so for instance, in Cartesian coordinates, we know that EX cross EY is equal to EZ, right? You can see that here. Sorry, I guess I can just draw these axes. This is X and this is Y and this is Z, right? You know from the right-hand rule that EX cross EY is always equal to EZ, right? And so that's why when I wrote a point here, I always write it as X, Y, and then Z, right? So we write X, Y, and Z. Okay? In this diagram right here, perhaps you guys can see that ER cross E theta is equal to EZ, right? That's always going to be true. ER cross E theta is equal to EZ. So that's why we call it R theta and Z. Okay. And once we do that, what that means is that if we were to if we were to assign numbers to these axes, that's why I didn't want to write 1, 2, and 3 here. You could call ER as E1, E theta would be E2, and EZ would be E3. Okay, does that kind of make sense? If you were to do that, then this relationship, which you guys have seen before, totally works out as well. Okay? This relationship is what gave us all the other cross-product relationships. For instance, applying this relationship, you will find that E theta cross EZ is equal to ER. Okay? Now, because the unit vectors here are not constant with respect to position, you have to be really careful when you take derivatives and integrals and stuff. Okay? That'll come up, like, especially later on in the class when we're talking about like flow around a sphere and stuff like that. And you have to like integrate velocities and integrate or take derivatives of velocities and evaluate shear stresses and stuff like that. This becomes quite important, right? So I'll just say, be careful about derivatives and integrals because the unit vectors depend on position. Okay. So in Cartesian coordinates, you would almost never write dEx dx, because that doesn't even mean anything, because Ex is just always constant. It doesn't matter where you are. And so this is just equal to 0, right? Because Ex is constant. But that's not true when we're dealing with cylindrical coordinates. You could take a derivative of ER with respect to theta. That derivative, all you have to do is come up here to ER and then take a derivative with respect to theta. Okay? So if we were to take that derivative, the derivative of cosine is negative sine, and the derivative of sine is cosine. And so we have negative sine theta, let me write a sign better, times Ex plus cosine theta times Ey. And what you find then is, hey, this is the same as this, right? This is E theta right here, and this is that. And so actually the derivative of ER with respect to theta is E theta. Okay. Perhaps that kind of makes sense intuitively, but I try to intuit these sorts of things, and it's really nice to be able to think about this, spatially and stuff. But these sorts of spatial visualization things can get confusing very, very quickly. Okay, and so just follow the math, and as long as you apply all the rules of calculus correctly and stuff, you'll get the right answer. But if we wanted to think about it, right, what the derivative of ER with respect to theta means is that if I have a point that's moving along the theta direction, what I'm asking is how much is ER actually moving, right? What's the change in ER if I'm moving in the theta direction? Well, it's changing E theta, a magnitude of E theta as I'm moving in that direction, right? Maybe you can see kind of directionally it makes sense, right? If I'm at a point here, my ER is going to point in this direction. If I'm at a point, let's say somewhere over here, then my ER is going to point in this direction. And if I subtract those vectors, then that goes in the direction of theta. Okay, maybe kind of makes sense, maybe not. All right, but mathematically, that's exactly how it works. Okay, let me give you just one more example. Derivative of E theta with respect to theta. E theta is this, right? And so, take a derivative of this with respect to theta. Derivative of sine theta is negative. Negative sine theta is negative cosine. Cosine is negative sine. So I have negative cosine of theta times EX minus sine theta times EY. And so that's actually negative ER. And again, you can kind of intuit and spatially visualize what that means. But again, that's exact. But the math doesn't lie to you if you actually did all the rules of calculus correctly. Let me give you an example of how you could potentially do the rules of calculus wrong and how we could actually do the rules of calculus correctly. Okay. Let's say we have acceleration of a particle. Okay. If we have linear motion of a particle, for instance, let's say that the speed of a particle can be given by s of t, and the velocity, and that particle is always moving in the x direction. It looks like that. Wow, this doesn't look good at all. Okay, s of t times ex. Okay, so what this just means is that sorry, not the speed of particle. It's the position of a particle is just going to be e. It's just going to be s of t, and it's going to move along x. Or I guess yeah, the speed of the particle is going to be s of t as it moves along x. Okay, the acceleration of this particle is the derivative of velocity, right? And the derivative of velocity looks like this. ds dt times e of x plus s times dex dt. Right? Now, we almost never write this other term here. This term, all I did here is just I applied the product rule to this. Right? We almost never write this other term here because this term is just always constant because ex is just always pointing in the x direction. This just goes to 0. Right? And so, as you might expect, the acceleration of this particle is just the derivative of s, of the speed, in the x direction, same direction as the velocity was. Okay, does this kind of make sense to you guys? Nod your head if this makes sense, shake your head if it doesn't. Makes a lot of sense, right? I'm telling you guys something that you guys already know, right? Now, what if instead the particle is moving circularly? Circular motion. Okay, let's say, well, the way that we would write that then is that it's moving at some speed, but it's always moving in the theta direction. Right? Going back to this diagram right here, if it's always moving in the theta direction, then it's always going to be parallel to e theta, regardless of where it happens to be. And then the instantaneous speed is just going to be s of t right here, right? Okay. The acceleration is, again, the derivative of velocity here. And so that derivative is ds dt e theta plus s times dE theta dt. Okay? And so doing it wrong, not following the rules of calculus, you would have not had the second term here. But now you realize that E theta actually depends on time because it changes as you're moving around the circle. Okay? And so let's actually figure out what that is. dE theta dt could be written as something like this. By the chain rule. Right? Now we calculated what dE theta d theta is. That's this. So that's negative ER. And d theta dt is just the change in angular position with respect to time, right? And so therefore, that's the angular speed. S of t is the linear speed. And so if you divide that by r, that gives you the angular speed. That gives you how fast theta is changing with respect to time, right? And so therefore, my acceleration is just, well, this right here. ds dt e of theta. And now I have something in the r direction as well, right? I have s times er times s over r. So I have minus s squared over r times er. Right? And so sometime in high school physics or college physics or whenever you took physics, your professor or teacher or something probably made a big deal about how centripetal acceleration is v squared over r, right? That's what we just showed over here. Okay? If we have circular motion where s here is constant, for instance, something is just moving in a circle at a constant speed, then my acceleration is always going in the negative er direction, always in the negative r direction, and the magnitude is equal to s squared over r. Now, if my particle is actually accelerating or if it's changing its speed, then you have this additional component here, right? And so just by showing stuff in cylindrical coordinates and knowing that we have different vectors and stuff in the cylindrical coordinates and taking a couple derivatives, you've already derived centripetal acceleration right here, right? So this guy right here, let me just write down, is centripetal acceleration. Okay, does that kind of make sense? Had anyone ever thought about centripetal acceleration this way before? I always thought this was kind of cool, right? I was just playing around with this and then, okay, anyway. All right, that's how unit vectors work. Just, again, you have to keep in mind, you always have to make sure that you're doing the rules of calculus correctly. You know, unit vectors can potentially change, and so you have to take their derivatives as well, okay? As a consequence of that, when you do things like gradient, the divergence, the curl, those are all a little different, okay? I'm not going to derive all of them. It gets complicated really quickly, and it's just all a bunch of geometry, and it's not really that pertinent to this class. Just look it up, okay? So I'll just say look at Dean section A.7. Okay, that has a great just appendix and table of how all these things work. Just to give you a quick preview, the gradient of a scalar actually looks like this. The divergence of a vector in cylindrical coordinates looks something like this. Like that. Okay, so it's not like before where we could just think about the del operator as like ex times d by dx plus ey, et cetera. Here, things actually get complicated, okay? You know, you can't really think about the del operator as like er times d by dr plus 1 over r e theta times d by d theta or something like that, because when you actually apply it to different things, you don't, like when you actually dot that operator to like a vector, you don't actually get the result, the direct result of that. So just look it up. Okay. One quick sanity check, kind of like earlier when I said, you know, when sanity check about solving a different equations, you have to make sure the boundary conditions actually match up and stuff. Here, one sanity check is just check the units. Okay. Here's what I mean when I say that. You know that r and z have to have units of length. Theta has no units, and so you have to have a 1 over r in front of it, right? Or like the derivative of something like this. It's going to be the original thing divided by length because it's a derivative with respect to z, or it's a derivative with respect to position, right? And so everything here has to have units of 1 over length with respect to vz, right? So this says this is velocity over length, if assuming v is velocity, right? This derivative here does not have units of 1 over, this is just velocity, and so you have to have a 1 over r in front of it, or something like that. So I'll just right here check the units. Okay. And then the last thing I'll mention is that integrals are also a little different, right? The volume element, when you do a volume integral, actually looks like this, right? But if you guys have done volume integrals and stuff in cylindrical coordinates, perhaps you've seen this. Surface integrals are also a little funky when you do it in different coordinate systems. Okay. And you guys have all seen spherical coordinates. And the stuff that I'm going to write down is pretty analogous, and so I won't go too much in detail with that. I'll just mention very briefly spherical coordinates. Okay, my handwriting is getting worse and worse as the class is progressing. I'll just mention very briefly that there are different conventions for people in spherical coordinates. We're going to use this particular convention, which is what the book uses. If I have a particular point like this, people like to call, or the radius, distance from the origin, is going to be given by r. This is my x, y, and z. Okay. The polar angle, or angle with respect to the z-axis, is going to be called theta. And then, of course, the other angle, which is called the azimuthal angle, is going to be called phi. As a result, you also have unit vectors and stuff like that, right? Anyway, this particular point is going to be written r, theta, and phi. Okay. The reason why I just had to make a big deal out of that is because different sources use different conventions. For instance, some places call r actually rho. Some places actually switch theta and phi. It gets really confusing. I don't know why people can't just agree on a standard thing. It's like the metric system. Okay. But Dean is going to use this, and so we're going to use this for the rest of this class. Okay. And we won't use spherical coordinates too much for the next couple weeks. But later on, when we're dealing with like flow past a sphere and stuff like that, these things actually will become important. Okay. So just really quickly, the conversion factors look something like this. Okay. Because we write down the coordinates as r, theta, and phi, then the unit vectors again obey the right-hand rule. There are unit vectors in this particular case. For instance, R, the direction is pretty obvious. It's just pointing an increasing R. Theta, the direction looks like this. E theta points in this direction, right? Because that's the direction of increasing theta. Okay. And then phi, it's hard for me to draw here. I'll just say it goes in that direction. It's the direction of increasing phi. It's supposed to go into the page a little bit, sort of looping around, going into the page. And that's why if you look at the right-hand rule, then E cross R, or sorry, ER cross E theta is going to be equal to E phi. Okay. And then of course, like, look up what the unit vectors actually are. There's no reason for me to write them down over here. But also, I just want to point out that the volume element can get even more complicated. This is where you start getting into like the R squared sine thetas and stuff like that. Okay. Questions about how this works? Obviously, the reason why I introduced this is because next lecture we're going to be dealing with a problem in cylindrical coordinates. Okay, questions at all? All right, if not, I will see you guys on Wednesday.